Hello students, I am Dr. Rajaram Dhok from Savitribai Phule Pune University affiliated Agricultural Development Trust Shardabai Pawar Mahila College Sharda Nagar Baramati. Let's start. We learn about the crystal field theory lecture 6. In this lecture, we discuss the crystal field spectra and measurement of 10 dq. So in the splitting of d orbitals, we have seen that there is formation of two groups of energy, that is T2g and Eg orbitals, and in between that energy is 10 dq. This 10 dq energy is measured in the form of spectrum, and from that spectrum we can measure the actual values of that 10 dq or stabilization energy. So for the crystal phase stabilization energy, there are certain evidences. So what are that evidences? So we see by using the certain examples. So this crystal phase stabilization energy plays an important role in the thermodynamics properties of transition metal compounds. There are many complexes of these transition metals, and these are stabilized due to the crystal phase stabilization energy. So there are some transition metal compounds, and that transition metal complexes with D0 case, D5 case, and D10 case, they have no CFAC. So we have seen in the last lecture, in the calculation of CFAC in D0 case, D5 case, and D10 case, crystal field stabilization of energies values are 0. So these compounds shows regular gradations or regular increase in properties like lattice energy and heat of hydrations. However, the transition metal compounds having configuration that is D0, D5 and D10 shows irregularities in these properties. Means in D0, D5 and D10 case, there is not increase in CFAC value, but in other cases, the values of CFACs are increased. So for studying this, we see the graphs. So in the figure 6 shows that a graph of lattice energies of the dichlorides of the metal from the calcium to zinc. And we see this figure. In this figure, we can see the at the x-axis there are different metals are given, and that metals lattice energy is calculated, and that is shown at the y-axis. Now the different metals lattice energy, corresponding lattice energies values are plotted, and after that the graph is prepared. So when that graph is plotted, then we get the values of different metals on this. Now we see in the D0 case, D5 case and D10 case, the values of CFAC is on the straight line. But in the other cases, that is D2, D2, D3, D4, then D6, D7, D8 and D9 case, values are not on the straight line, that is more than the straight line. And this shows that with the CFAC, there are some other energies, or with lattice energy, here there are some other energies, and that is the CFAC or crystal phase stabilization energies are present. And so this shows that here in this lattice energy, other energies, that is crystal phase stabilization energy is present, and because of this, these values are higher. Now, if we remove this crystal phase stabilization energy for D1 case, D2 case, D3 case, from this lattice energy, then its value is on the straight line. And this proves that here with this lattice energy, there is crystal phase stabilizing energy is present in that different dichlorides compounds of calcium to zinc. So these observed energies are shown by the circles, and this energy shows such type of increase in the properties. So we see the crystal field spectra and measurement of 10 dq. In that, we studied about the absorption spectra of complexes. This absorption spectra of complexes enables to find the values of 10 dq. And here bands are observed, or absorption spectra can be related to the excitation of these electrons or electron between d orbitals, and that is called as dd transitions. So such type of electron between d orbitals split by the crystal field, and these electrons have ability to interpret such spectroscopic evidences, and that is one of the advantages of CFT. Now we see the one other example, that visible absorption spectra of titanium hydrate, that is TiH2O6 3 plus. This complex ion is given, and in this case, when we measure the spectrum, then on the x-axis there is given the frequency in centimeter raised to minus 1 into 10 raised to minus 3, and on the y-axis there is shown the molar absorbance. So we get here the particular peak, and it shows the values of that particular compound, that is TiH2O6 3 plus. Now we see here the calculation of this. So in this case, we consider that the octahedral complex TiH2O6 3 plus, and in this complex it offers a simple case, and it has only one d electron, because in this compound d1 case is present. So in the ground state, the electron will occupy in the one of the T2G orbitals, but absorption of transition will excite it into the one of the EG orbital. Means from firstly one electron is filled in the T2G orbital, and by the excitation, by absorption, it is transmitted to the EG. And so T2G to EG transition is carried out, and here such type of transition is expected. The energy difference between T2G and EG is 10 dq or delta O. This is already we have discussed. So this absorption band due to DD transition in this TiH2O6 plus 3 complex ion, that is observed in this figure, and that we have seen, and that absorption gives here values 20400 centimeter raised to minus 1, or in case of the degree Armstrong 4900 degree Armstrong. So absorption peak in the figure we have observed, that is 4900 degree Armstrong. Now we can calculate this crystal field spectra, or with the help of spectra, see crystal field spectra, the 10 dq values, and for that purpose we use the famous Einstein's equation E is equal to, or energy is equal to h nu, or energy is equal to hc nu bar, and here h means the Planck's constant, and we know the value of Planck's constant 6.624 into 10 raised to minus 34 joule molecule raised to minus 1. Then C is equal to 3 into 10 raised to 10 centimeter second raised to minus 1, that is the velocity of light, and nu bar means that is the absorption band, that is 20400 centimeter raised to minus 1. So these all are taken in the same unit, so we take this wavelength in the centimeter raised to minus 1. Now substituting these values in the equation energy, so we can get energy is equal to 10 dq. So we know that E means that is the 10 dq. So that 10 dq is equal to hc nu bar. So we add the values of hc nu bar, that is 6.624 into 10 raised to minus 34 into 3 into 10 raised to 10 into 20400, and by solving this we get 4.054 into 10 raised to minus 19 joule molecule raised to minus. Now after that we find out the energy per mole. So by multiplying the Avogadro's number, we get these values per mole. And so we multiply 4.054 into 10 raised to minus 19 by Avogadro's number, and Avogadro's number value is 6.624 into 10 raised to minus 34 joule mole raised to minus 1. And by calculation, we get 244.2 kilojoules mole raised to minus 1. Now, this kilojoule we can convert into the kilocalorie. And for that purpose, by converting, we get 58.35 kilocalories mole raised to minus 1. Means this 244.2 kilojoules mole raised to 51 or 58.35 kilocalories mole raised to minus 1. These are the values of delta, or these are the values of 10 dq. Means with the help of spectrum, with the help of given spectra, we can calculate or we get the values of 10 dq. So in this example, TiH2O6 2 plus, the light of frequency 20400 centimeter raised to minus 1 is green, and if such light is absorbed, the transmitted light appears violet. The transmitted light appears violet. So this TiH2O6 3 plus complex looks violet colored. So here this DD transition in the TiH2O6 3 plus and the values of 10 dq we can calculate very easily. So you see this diagram, that is for simplicity. Already we have discussed that one electron is present and that one electron is filled in the T2G, one of the T2G orbital, and when they are transmitted from T2G to EG, then that energy is 20400 centimeter raised to minus 1, which is just we have used for the calculation. So this is also the DD transition.